So good morning student. In the last video we defined what is meant by an open ball with center A and radius R, and we give one example, one example of open ball, and that is in R, set of real numbers with the usual metric. The open ball center at A, the radius R is exactly A minus R comma A plus R, the open interval. So with that help we can go further. So what is how to define an interior point of a set? Still we are dealing with only metric space. You take x comma d as a metric space and A any non-empty subset of x. You can then take a point x in A. With regard to this set and a point in that set, we are going to define what do you mean by an interior point? What do you mean by an interior point? So x in A is said to be an interior point of A if there exists or positive such that ball with the center x, radius r is completely contained in A. I will explain. A point in a given set, a point x in a given set A is said to be an interior point of that set A if corresponding to that x there exists some r positive, such that the open ball with center x and radius r is completely contained in A. We know the definition of an open ball with center x and radius r. What it actually b of x comma r. In the last video we have defined it as collect all possible points in a metric space. This line is very essential. Many of the students are forget what to write in that place. It's not traditional to write y belongs to x always. With respect to the metric, you are defining the open ball. B of x comma r means that you collect all possible points in that given metric space under consideration, whose distance from the point x is less than r. Again, I insist the definition. You collect all possible points y in the metric space, in that metric space x, such that d of y comma x, that is distance from y to x, is less than r. So that is the definition of open ball. If you want to say that x is a point in a set is an interior point. So given a set and a point in that set, if you want to say that the point is an interior point of that set A, if the following condition true, that is, it is possible to identify at least one positive number r such that ball with x with that r positive is contained in A. So every it doesn't mean that every radius r positive obey this property. At least we are able to identify one positive number with this property. You say that the corresponding point x is an interior point of the given set A. We can give some example of an interior point of the set. Just like when we define the open ball, in R, we take here also the metric space as the set of real numbers R with the usual metric b of x comma y is equal to mod x minus y. Distance between any 2 points x and y in R is defined as mod x minus y. And we take the set A as for example, the point 1, 5, 7, 10, 12. This is my set A. So I want to verify whether any of these points 1, 5, 7, 10, 12 are interior to this A. I want to check that. First you take the point 5. It is in A. First condition, you have to verify whether it is a point of A. Yes, it is a point of A. To talk about whether it is an interior point of A. Then I just draw the real line to elaborate this concept. 1, here is 5 and 7, here is 10 and here is 12. Okay, I am considering this my point x. So what is the condition I have to verify? So a point x in the given set is said to be an interior point to that set if there is a point, the positive number r. With that positive real number, if I consider this ball with center x and radius r, it should be a subset of A. So we know that you can give any positive number. For example, if you take a positive number r equal to 0.2, r equal to 0.2. So, and what is this set? Ball with center 5, radius 0.2. In the last video, we proved that actually it is an open ball. Okay, it is an open ball. X minus r to x plus r. Okay, that is 4.8 to 5.02. An open interval 4.8 to 5.02. So look at that, all these points 4.8. Okay, 5.2. So this is my open ball. The point I shared. Okay, this is my open ball. That is not including 4.8, not including 5.2. So what is the criteria? So here is one example I am saying that r equal to 0.2 were taken. Okay, for the 0.5 and consider the open ball center at 5 and radius 0.2. In the earlier discussion we have proved that it is an open ball of the type x minus r to x plus r. Here x is 5, so 5 minus 0.2 to 5 plus 0.2. So it is obtained that 4.8, 5.02 is an interval. Okay, 5.2. Okay. And note that here there are many points in that interval, in that open ball, okay, which are not in A, okay. So this is definitely not a subset of A, because A consists of only 5 points, 1, 5, 7, 10, 12. Okay. So here for this radius, if you consider the corresponding open ball centered at 5, okay, it is not a subset of A. And I am putting this radius as for intuitively one radius positive. You can give any number r positive. Here instead of 0.2, you can take any r positive. Okay, any r positive. Here we are getting 5 minus r to 5 plus r as an open ball, and still it is obey the property. It is not a subset of A. It's not a subset of A, because for any r positive, okay, 5 minus r. Okay, for any r positive, 5 minus r will be here and 5 plus r will be here. Okay, there are points inside this open ball which are not in A. Therefore, the point 5 is not an interior point of A, because we have the property that for the point 5, you can give any r positive, the corresponding open ball, okay, the corresponding open ball with the center 5, radius r, okay, will not be a subset of A. Okay. So what we must have is, we are expecting is, for the point 5 in A, at least one positive number should obey this property. That is, ball with center 5, radius r will be subset of A. But here the fact is, given any r positive, the corresponding open ball is namely 5 minus r to 5 plus r is not a subset of A. Therefore, this 5, the point of, even though it is a point of A, is not an interior point of A. It's not an interior point of A. Instead of 5, if I take 1, or if I take 7, or if I take 10 or 12, okay, the same argument will illustrate that none of the points in A is an interior point to A, because instead of you are taking 1 and use the same argument, you can have that maybe if the point is 1, 1 minus r, 1 plus r is not a subset of A, and 7 minus r, 7 plus r is not a subset of A, and 10 minus r, 10 plus r is not a subset of A, as well as 12 minus r, 12 plus r is not a subset of A for any r positive. That means none of the points in the set is an interior point to that set. Okay. Next, you can take, instead of A as this finite set of point, you take this one, interval 1 comma 5, open interval, left close interval 1 comma 5. Okay. And you take the point 1 belongs to A. Here the point 1 belongs to A. So similarly, similar argument, okay, for any r positive, if I consider ball with center 1 and radius r, it is precisely the interval 1 minus r comma 1 plus r. We know this. Okay. So here the set actually 1 to 5, and the open ball center at 1, radius r. So here I insist one point. When you consider the open ball, okay, at point x, you bother about the what is the metric space you are considering. Okay, don't bother about the set you are considering. Okay, to write the open ball. Okay, so b of 1 comma r means, what is the b of 1 comma r? It is 1 minus r comma 1 plus r interval, because the metric is usual metric and the space is r. Okay, so here the 1 minus r comma 1 plus r. Okay, look at that. This open bar contains points which are not belongs to the set 1 comma 5. Okay, here there are many points. There are uncountably many points. Okay, which are not in 1 comma 5. That means ball with center x, radius r is not a subset of. Here x is equal to 1. For the point 1, you can take any radius. You can take any radius. The corresponding open ball with radius r center at 1 is not a subset, because every time when you give a positive number r, every time the left portion, the 1 minus r to 1, okay, is not a subset of this set 1 comma 5. Therefore 1 is not an interior point. So this implies that the point 1. So here for the point x equal to 1 in the set A, okay, for any given r positive, the corresponding open ball with center 1 and radius r is not a subset of it, because every time when you consider the open ball center at 1, okay, you are considering the matrix with the whole r. Okay, that means the ball is 1 minus r to 1 plus r. So the left portion 1 minus r to 1 contains many points which are not in this set. Therefore, so b of 1 comma r not a subset of A for any r positive. For any r positive, which means that the point 1 in A is not an interior point. Not an interior point of A. Now you can take the other point. Okay, instead of taking 1, if I take the point nearby 1, so will it be an interior point for A? Will it be an interior point for A? So we will explain. So here the set A is having 1 as a leftmost point, 5 is rightmost point, 1 is included. Instead of 1, you can take any other point. Suppose I am taking this point, okay, as x. So our aim is where this x is an interior point of the given set A. Okay. First condition, you must verify that the point must be in that set. So here x, I am taking the point between 1 and 5, therefore it belongs to A. X is in A. Okay. Now geometrically, or maybe intuitively, if you look at it, is it possible to draw an open ball, an open interval around x which is completely contained in the set? Is it possible? Because what I think is it possible to draw an open interval around x, symmetric open interval around x, which is completely contained in A? Why I am asking that open interval, symmetric open interval? because in R usual metric, with respect to usual metric, ball with center x radius R is actually x minus R to x plus R. Okay, it is a symmetric interval around R. Okay. So given a point x in A, so if you look at this picture, it's anybody can answer this question. If you choose this amount as R, this length as R, then x minus R to x plus R is completely contained in the set A. How to choose this R? So the idea is you are taking actually this distance, okay, pictorially this distance and this distance, okay. You don't consider this one, you are considering this alone and choose the smaller one, because if you choose R radius as a very large one than this distance, then it will cross 5, okay. Or first thing, if you choose this large amount as a radius, large distance, that is 1 and x minus 1 as the radius, and the interval, okay, left side no problem, okay, left side no problem, right side it will cross 5. So the intuition will lead to the fact that how to choose the R positive. Okay, the idea is very clear. You are finding actually distance from x to 1 and distance from 5 to x, and whichever is minimum, you choose that minimum and less than that minimum. Okay, so here is the idea. I am going to choose R as a number, positive number less than, okay, minimum of the two distances, 5 minus x and x minus 1. Okay. So minimum of two distances, 5 minus x and x minus 1. So these are two positive numbers, both are positive, and therefore minimum is positive, and you are choosing a number which is less than that minimum of these two numbers. Okay. Definitely ball with center x with this radius R is your x minus R to x plus R, containing the interval 1 comma 5, interval 1 comma 5. We are considering actually this x minus 1 distance and 5 minus x distance and choose the minimum. So in this representation, this 5 minus x is a minimum number. You choose a number which is less than this 5 minus x distance as R, okay, and your R distance is now this one, and the respective x plus R will be here and x minus R will be here. The interval is actually a subset of 1 comma 5. Okay. That is, if you choose R in this manner, the corresponding ball with center x and the respective R positive is subset of 1 comma 5, which means that we are able to identify there is R positive such that ball with center x radius R is subset of the interval 1 comma 5, which is our set A. So for the given point x, okay, there is a positive number, the corresponding open bar is contained in A. Therefore, this point x becomes an interior point of the given set A. So you can take instead of A, you can take here, no problem at all. This one. So whatever point you choose in between 1 and 5, not including 1, the respective open bar of this radius will definitely a subset of 1 comma 5, which is your set A. That means the point x other than 1 in that set becomes an interior point for the set A. So here is an idea for the next definition. Okay, the interior of a set. Okay, given a set, and you collect all possible points which are interior to the set A. So for the set A, okay, you identify all possible points which are interior to the given set A. Okay, that is defined as interior of the set A and denoted like this, int, interior of A. So what it actually means, it consists of, it is a set actually, it consists of those points in A such that those points in A which are interior to A. Okay. That is, it consists of all interior points of A. Okay, it consists of all interior points of A. Actually, what is the property that a point in this set should obey is given that point. So if I take a point maybe y in A, y in interior A is given, then what are the properties that y has? Y must be a point of A, and then y is an interior point of A. That means y is in A, and for that y there is a positive radius such that ball with center y with that positive radius is completely contained in A. So that is the property the point y has. Okay. You collect all such points y, put it in a set, and say it is a definition of interior of A. Okay. And the previous examples, the first one is A is 1, 5, 7, 10, 12. None of the point is an interior point of A. Therefore, in that case, interior of A is an empty set. The second one, when I take A is equal to left close 1, 5. Okay, the interior of A is the open. So interior of A is open interval 1, 5. That is the point 1. Though it is a point of A, it fails to satisfy the interior point of A. Therefore, other than the point 1, okay, all the points obey the property that for each such x in that set A, okay, there is an R positive, such that ball with center x radius R is completely contained. Therefore, all the points except 1 obey the property for an interior point of A. Therefore, interior of A in this case is the open interval 1, 5. So there are many properties of interior of any one set. Okay, we can look at it in the next session. Okay, thank you.